Okay, today we're going to start with Vesper Theory. Vesper is an acronym that stands for valence shell electron pair repulsion. So when we draw the Lewis structures for molecules, like we learned about yesterday, we draw them in a two-dimensional space just with bonds and lone pairs. But in real life, because of electron repulsion, those bonds and lone pairs repel each other because they have negative charges, and their repulsion leads to three-dimensional shapes, to different shapes. And that's what all of this is. An example, NH3 if we draw the Lewis structure for NH3, nitrogen has 5, each hydrogen has 1, it ends up looking like this. We have 2, 4, 6, 8 electrons, and all of them have a full octet. Hydrogen doesn't necessarily have an octet, but it has a full outer energy level with 2. 2. Hydrogen only gets 2 electrons to fill its energy level because it only has 1 energy level. And that first one only holds 2 electrons. But this is not what this would really look like. The electron locations in NH3 and ammonia are actually farther apart. So if we measure the bond angle of this, these are all 90-degree angles. But because of electron repulsion, this lone pair of electrons repels the single electrons in hydrogen, and they all get pushed down and away from each other because they're repelling. That's what electrons do. And you actually wind up with something that looks more like this, with one of them going into the board in a three-dimensional space. And our bond angle is now bigger. It's 107.5 instead of 90. The electrons are farther apart.
Wait, how did you know that?
Because I've memorized it like you're going to. So we would call this trigonal pyramidal. And the shape, you always base it on the central atom and what's on the central atom. On this central atom, there's a single lone pair and 3 bonding areas. If you look at this table, 3 bonding areas, 1 lone pair is trigonal pyramidal for your geometry of atoms, and it has an angle of 107.5. That 107.5 can vary a little bit based on what atom is out here. If these were chlorine atoms, that angle might be a little bit bigger because they would push even more against each other. You might get 109 or something like that. On the AP test, they're always going to accept a range. Usually a 5-degree range is correct, like 105 to 110 or something like that. So, what you have to do, you have to memorize if the central atom has this many bonding areas and this many lone pairs, it's this shape and this angle. And I would make flashcards because you're going to have to know this. You can always draw the Lewis structure in 2 dimensions. You'll never be expected to draw it in 3 dimensions. but you will be expected to know what the shape would be. Yep.
Are we gonna be? Is this gonna be our test?
Yep.
Yay.
Okay. But when we talk about bonding areas, we have to be careful. So if we look at carbon dioxide. Carbon dioxide has 4 and 2 times 6. So 16. That's 2, 4, 6, 8, 10, 12, 14, 16. I filled them all in, but I don't have a full octet on carbon. So I have to double bond. That's my Lewis structure for carbon dioxide. But when I go to find my shape and I have to count bonds and lone pairs, this is counted as one bond. It's more like a bonding area. Number of things bonded to the central atom is what you're counting. So this has 2 bonds and 0 lone pairs. So we would call it linear, and it would be a 180-degree bond angle. Yep.
How do you know how many lone pairs it has?
The dots, once you've drawn it correctly. So like this one had 1 lone pair. Once you draw the Lewis structure the way you learned yesterday, and then you would count how it ended up.
So on here, what are the thicker lines mean?
They're trying to show 3 dimensions. So like a thicker line is coming out of the board,
Oh.
a dashed line is going into, and the single line is just parallel on the paper. They're just trying to show 3 dimensions. Good questions. So, the way I would do this, and I have done this a long time ago, is I would make flashcards. I don't care how you make flashcards. A lot of you like to use Quizlet. I also have used Google Slides. Oh, I need to erase. If you go to Google Slides, at the top there's a template already made for flashcards. That's already there. You can just edit them, so that's the Spanish quiz, that's what it will look like. But I have edited them to make Vesper flashcards. And if you do the presentation, the first one says if it has 2 bonds and 0 lone pairs, it's linear and it's 180 degrees. Those are the things you need to know. So, bonds and lone pairs tells you the shape of the molecule, or the shape of the atoms, and the bond angle. That's the information to memorize. Jonathan?
Can we access that?
I used the Spanish one and I just edited the first one.
Oh.
Just look.
Oh.
Yeah.
Look, it's really fun. But you can just make your own. You just have to change it.
Come on, you know I got this one right now.
Okay, so make your flashcards. You really only have a week to memorize that because your test is next Thursday.
Yay!
Start working on it.
I love
So
school.
excited for this test.
Okay,
Quiz.
the next thing I want to talk about is hybridization. I'm going to shut off like this. Hybridization. What does a hybrid just mean in general? Have you ever heard of a hybrid before?
Combining 2 things.
When you combine 2 things, you have a hybrid. We've talked about hybrids in biology. When you learned about genetics, you talk about hybrid pea plants, for example. If you ever watch sci-fi movies, sometimes they talk about hybrid creatures where you combine 2 different creatures to make some new super powerful creature. In chemistry, hybridization is not so exciting. It's the combining of sublevels to make different sublevels, to make orbitals. So combining sublevels to create unpaired electrons. This is a little bit confusing. So if we look at what we did yesterday, boron trifluoride, and I draw the same boron trifluoride that I drew yesterday. We're focusing on boron here. Boron is making 3 bonds. And in order to make 3 bonds, there have to be 3 lone electrons. 3 unpaired electrons in the valence shell. But if we look at this for boron, the orbital diagram for boron, it looks like this. 1s2, 2s2, 2p1. And according to this, boron only has 1 unpaired electron to form a bond. But it's forming 3 bonds. What happens is boron's S and P sublevels hybridize their orbitals to make room for unpaired electrons. So if these 3 orbitals hybridize into a new sublevel called sp2, these 3 electrons can spread out and be alone, so they're able to bond. That is hybridization, where this orbital and these 2 orbitals combine to make a brand new sublevel called an sp2 sublevel. And this is called sp2 hybridization. The S is because there's a single S, and it's P2 because 2 of the P's are here. To make 3 unpaired electrons that are available to make bonds. Without hybridization, boron could not bond 3 times. Okay, let's do another one. We also did methane yesterday, CH4. We're focusing on carbon here. We look at the energy orbital diagram for carbon. It looks like that. And according to that, carbon can only bond twice. But carbon is bonding 4 times. So, we hybridize and make an sp3 sublevel so we can have 4 unpaired electrons. Elise?
Why was boron trifluoride called SP2 and this one called?
Because the boron trifluoride only used 2 of the P's. This one is using all 3 of the P's. The superscript is just telling you how many P's are involved.
Okay. And can only 2 sublevels combine? Or
Yeah. I mean, for now, in AP chemistry.
What's the chemistry?
So SP3 is when something's making 4 bonds. What was your question?
How does like this happen in like a lab setting? Like say you hybridize something.
It doesn't happen in a lab setting. It happens in a nature setting. The electrons just naturally get on kind of the same level and they unpair. It happens completely on its own. We don't do anything to make it happen.
Is it like just a instantaneous thing?
It's just a natural thing. Like it just happens when carbon goes to make bonds.
So it only happens when they're in the bond form. Like,
Right.
okay.
Okay.
So instead of having the 2s and the 2p, then it just has the sp3?
They just combine into an sp3.
Looks like SP4.
Okay.
That would
Like
be
those things that Napoleon Dynamite draws,
Yes.
where the liger, the lion, and the tiger just combine into a liger.
What?
This is like that. They just combine into one thing.
Yeah.
I'm still a bit confused. Why does it do that?
We don't know why it does it. All we know is it does do it because that's the only explanation for why carbon makes 4 bonds.
So it's like
So really what happened is chemists said, oh, this is what carbon is. And then chemists said, oh, this is what methane is. And those 2 things didn't go together. They didn't match. So they theorized that this must be the case. It's a theory.
so.
Okay.
What if it's like a 2p3?
Why wouldn't, or do you know why wouldn't carbon be able to make the bond like normally?
Well, looking at this, unpaired electrons make bonds. You don't have a paired electron making bonds. So they have to be unpaired. And this is the explanation we came up with.
Okay.
That's the best I've got. Elise?
So it's kind of like the 2s just moves up. So you said like it only uses 3 of the p slots, so that 4th one is the s slot.
Right. And not necessarily, don't think of it as S moving up. I shouldn't have drawn this at the same level. It may be the P's and the S's kind of meet in the middle, but they all just kind of combine into one sublevel with 4 orbitals.
So what if it's like nitrogen and it's like 2p3? Does that hybridize with anything?
Nope, nitrogen doesn't. It makes 3 bonds.
So there's only certain elements that.
Only certain elements hybridize.
So only if there's like 1 or 2 electrons in the p.
Basically, yes. And it needs to make more bonds.
Why isn't that called like 2sp3?
It could be, but I was just trying to make it general.
Thank you.
Do we know which slot is like the s slots and which ones are the p? Like in that?
They're all in, everything's in constant motion here. It's all about averages. We could never define that. Because it's quantum theory. And in quantum mechanics, if you know the location of something, you don't know where it is, you don't know how fast it's going, we can't define that. It's undefined. Okay, so really what you need to know is if it's making or having 2 bonding areas, 2 bonds / lone pairs combined, that's sp hybridized. And the way that we know it's 2 is because the superscripts add up to be 2. If it has 3 bonding areas / lone pairs, that's sp2, because our superscripts add up to be 3. And if it's making 4 bonds or has 4 bonds in lone pairs, that's sp3. There are others. If you take more chemistry in college, you will learn about other hybridizations. But in AP chemistry, the only ones you need to know are sp, sp2, and sp3. Okay? And you count them. So in this, in the NH3 that we looked at earlier, this is also sp3 because we count this as 3 bonds and a lone pair. That's sp3 hybridized as well. It involves an S and 3 Ps. Okay. The last thing we need to talk about are sigma and pi bonds.
Sigma's just a weird sex.
When we're bonding two atoms, the first bond created between those atoms is the strongest bond, and that's called a sigma bond. It's the first bond formed. Sigma bonds usually originate in an s orbital. They don't have to, but they often do, and they're the strongest. Pi bonds are the later bonds. If a second bond or a third bond, a double or a triple bond gets formed, those are pi bonds. Second or third or even fourth bonds formed. And the pi bonding comes from the fact that p orbitals are in different planes. So there's a px, there's a py, and there's a pz. And pi bonds can be in different, they're spinning in different ways. They're spinning in different directions because you have x, y, and z. Don't worry too much about that. All you need to know is if something is single bonded, like this, they're all single bonds, we would label all of those bonds sigma bonds. The first bond formed is always a sigma bond. If something is double bonded, like diatomic oxygen, that we talked about yesterday, one of those bonds is a sigma bond, and one of those bonds is a pi bond. Now everything is in constant motion. We could never define which is sigma and which is pi, but we know one of them is sigma, one of them is pi. If something's triple bonded, like diatomic nitrogen, that diatomic nitrogen is created using one sigma and two pi bonds. And that's as complicated as I want you to get with sigma and pi. The quantum theory that's behind it is more complicated than anything you need to know.